All right, so I've set up this metaphor about bringing home the spoils of experimental success, and I've talked about how those spoils, so to speak, are mostly located in quantum field theory, or at least the route to bring them home takes them through quantum field theory, right? So why is it difficult to model measurements using quantum field theory? Why don't the existing solutions really do justice to this problem? Well, in most textbooks, measurements of quantum fields are discussed in terms of scattering problems, right? Here we have an electron coming in and a positron coming in, and they undergo some sort of interaction, and then you have to sum over all these Feynman diagrams consistent with this if you're doing it by that way. But roughly, the scattering particles come in, they interact in some way or some number of ways, and you get the total amplitude for then different types of outgoing particles. Here it's 2 photons coming out. And these outgoing particles are then picked up by some often undescribed detector. You sort of just take the squared amplitude of those emission things and say, oh, we can catch those and measure them, and it comes out to show us with the probability of the squared amplitude that that's what happened, right? So, however, as a growing portion of the physics community is becoming aware, and here's just some references which deal with this, and notice they're all from last year. This is really quite a hot topic in current years. Such hand-wavy models of measurements of quantum fields are deeply unphysical and unsatisfying. To explain this, I'd like to go through a scenario about Bob, who would like to explain his new experiment. So just let me take you through a little dialogue between Bob and Alice, and we'll see where that leads us. Right? Suppose Bob has a new quantum experiment that he wants to explain. And somewhere towards the end of that experiment, there's a piece of lab equipment which is localized in some region R big in space and time, which at first glance to Bob, his pre-theoretic intuition is that it appears to be counting the number of fast-moving electrons going through the space-time region R small, right? So he thinks this is roughly what his measurement device is doing. And Bob understands how to do projective measurements in non-relativistic quantum mechanics, but he really does not know much about QFT. Luckily, though, Bob has his friend Alice. She does know a lot about QFT. She's an expert in it. And also, we're going to assume here that Bob really doesn't want to give a model of his detection system, if at all possible. He'd really like to avoid that. This is his only vice. Everything else is going to go perfectly in this conversation, except that Bob will just refuse whenever asked to give a model of his detection device, right? So, we've got Alice and Bob. Bob's first thought here is that his lab equipment in R big tells him something like, or it can tell him something like, look, there are 3 particles in region R small, and they're located at x1, x2, and x3. And Bob thinks that this exactly determines what's going on in R small. He's found all the particles, he's found where they all are. He thinks that's an exact description of what's going on in this region R small. Again, Bob doesn't know much about QFT. So Bob goes up to Alice, who's an expert, and asks Alice if there's any projective operator in QFT which fits this description. He thinks maybe this is what his lab equipment does, and so if he can find the projective operator in QFT that fits, that would maybe answer his question. Maybe his measurement device just does this projective measurement. And that would be great for him, and he can plug that in, put it in his papers, and get published. Right? Alice takes Bob's request and says that no, actually, for actually quite a number of reasons, that sort of thing's not possible in QFT. In particular, she shows Bob this theorem here, which is discussed here in this paper by Redhead. In quantum field theory, all local projectors are of infinite rank. And this is the technical reason for this is that we now have a type 3 von Neumann algebra. But don't worry if you don't know what that is. So, since all human doable measurements are local measurements in space and time, they must also be infinite rank. And let me give a quick refresher on what it means when I talk about the rank of a measurement. Suppose that I measured the angular momentum of an atom, and I find the quantum number L is equal to 1. Then to update my state after this measurement, I should apply this rank 3 projector, which has a sum over L equals 1 and M equals 1, where M is the azimuthal quantum number, the z-axis quantum number, but M could be 1 or 0 or minus 1, because there's 3 states which are consistent with my measurement result. I have to consider all of these, and I project onto this three-dimensional space. That's why it's a rank 3 projector. Contrast this with measuring whether a quantum harmonic oscillator is in an even or odd state. This is an infinite rank measurement because it's going to leave an infinite number of possibilities open with any outcome that it gives, right? So it's an infinite rank measurement, or it involves infinite rank projectors. So what Alice is telling us is that in quantum field theory, all local measurements have to leave an infinite number of options open. Nothing that we can do in a local region will exactly determine what's going on in R small. So this is an issue with Bob, what Bob was telling us. So Bob here has learned a lesson. He's learned that in QFT, there's no measurement within a bounded region R big that can tell us the exact state in R small is whatever he claims it to be, right? So there's no such measurement in QFT. It goes against the algebraic structure of the theory. Is Bob's problem here then that he's tried to assume a mathematical maneuver which is banned by quantum field theory? He certainly has tried to do that, but is that really the problem? Or is it rather that he's being very hand-wavy about his measurement process, and when you are so hand-wavy, you're liable to make mistakes and do moves which are not licensed by the theory? So I think the problem's really two, but Bob really doesn't want to model his measurement process. And so Bob's going to pretend like the answer is 1, and he's going to look for a loophole. He's hit some mathematical snag, and he's just going to back up and try again and try and get around this mathematical obstacle that's in front of him. He doesn't want to change his methodology. He's not willing to admit that he's got a methodological issue here. He thinks he's got a mathematical issue. So Bob then comes to Alice the next day, and he asks her, is there a projective operator in QFT which could tell me there are 3 particles in R small, wherever they may be, right? And he thinks maybe this would leave an infinite number of options open and get around that algebraic infinite rank issue that I've mentioned. Unfortunately, Alice says to Bob, no, this still doesn't work. There are no locally defined number operators n hat of small R small in QFT. If you could reliably do this particle counting measurement, then you could build this number operator, and those things just don't exist in QFT. And she shows him some papers by Redhead and Malamant and other people who discuss this, right? But to summarize, Alice says roughly the reason for this, if you want some physical gloss on it, is because n hat of R small would have to count +1 particles for all of the particle-antiparticle pairs which are being produced in R small, right? And this would consequently diverge terribly. If you look at any quantum state and you look at it on very small scales, there's a soup going on there of particle production and everything, right? So you get a terrible divergence if this is allowed to happen, or if you try and count particles in this way. All right. Bob has learned a new lesson about QFT. He's learned that in QFT, there's no measurement within a bounded region R big that can tell us something like there are 3 particles in region R small. Okay. So Bob knows this isn't possible now. Is Bob's issue, again, that he assumed a mathematical maneuver banned by QFT? Is it a mathematical problem Bob has, or does he have a methodological problem that he's waving his hands about the measurement process? Right. Bob really doesn't want to model his measurement process, though, and so let's pretend the problem's 1, and let's look for a mathematical loophole that gets us around this issue. Right. And this is the last one of these I'm doing. So don't worry, the conversation ends soon. So Bob takes a week, and he goes and thinks, and he comes back a week later, and he says, Alice, I thought about what you said, and maybe we can fix the divergence issue if I count particles and antiparticles with different signs, right? Then pair production events will count as +0 overall, and therefore we won't cause a divergence, right? Bob says, maybe I was being uncareful earlier when I said that there are 3 particles in region R small. I should have said there are exactly 3 excess unpaired particles in R small, right? Because of course there's pair production going on, but there's always 3 excess particles, right? Those don't annihilate. Even if the annihilation happens, some other electron's produced, which goes on. So I think there's 3 stable excess unpaired particles in R small. I think that's probably what I meant to say. So I'm being much more careful now. Alice says that's very clever, yes, and actually that does solve the divergence issue. Good on you. But what you try and define a signed local number operator in quantum field theory, something else goes wrong involving the commutators at space-like separation. There's some other issue that comes up, and I don't want to continue this conversation between Alice and Bob much longer. The conversation continues on like this for a long time. Where is this process leading us to? What's really going on between Alice and Bob here? Bob, recall, all he's really looking for is a projector defined on some space-time region R big, which fits the description of the behavior he's seeing in his lab. He basically knows what his lab equipment does pre-theoretically, and he's just looking for a way to find something in QFT which matches onto that. This is all Bob wants. As this continues, Bob's going to learn a lot about QFT, which is great, really good for him. And he's going to be increasingly careful about the descriptions he makes of what he's looking for. This is really great, seems very pedagogical, he's learning a lot, it's a really good process. Maybe, ultimately, he's forced to stop talking in terms of localized particles. I think that's the case, but it's not important. It's not important if Bob learns that lesson or not, or if that's the right lesson for Bob to learn or not. He just wants this match with his experiment. Alice, what's she doing in this conversation? She just keeps telling Bob what is and is not well defined in QFT. And the best that she can do, in the limit of this conversation going on forever, the best she could possibly do is to provide Bob with a full menu of what it's theoretically possible to projectively measure in QFT. She could present this to Bob. Okay, let's go to the end of their conversation. Let's suppose this happens. And actually, this has happened. These references 9 and 10 are people doing just this, giving necessary and sufficient conditions. So suppose Alice provides necessary and sufficient conditions for what is theoretically possible to projectively measure in quantum field theory without breaking causality. I should mention this specific risk to causality because it's very important in the literature. It was raised by Sorkin in 1993, is that there's some well-defined measurements in O2. Here we have the space-time diagram, which has regions O1 and O2 and O3. O1 and O3 are in space-like separation to each other, so they shouldn't be able to communicate. But it turns out there's a well-defined projective measurement which you can do in O2, which will allow for signaling from O1 to O3. Right? It's well-defined and it breaks the causality of the theory. So it's obviously not physically allowed. Right? So there's these impossible measurements. That's the title of the Sorkin paper. There's these impossible measurements in QFT which we have to somehow avoid. Right? And so suppose she gives necessary and sufficient conditions for all of the projective operators which don't do this, which don't break causality in this way. That's what these papers 9 and 10 do. Right? So, as this conversation goes on, Bob now has his full menu of projective measurements which he can choose from. Okay? Alice has done all the work. Again, what's going on here? Bob has learned a lot of QFT. That's great for him. Alice has proven a beautiful, interesting theorem outlining the scope of what's possible in QFT. That's great for her. Everything's going very well. Bob now has a full menu of the projective measurements he can choose from. Bob can now find the one, or honestly, there's probably going to be many projective measurements which line up with the observed behavior of his lab equipment, right? So, is this case closed? Has Bob satisfactorily explained his experiment and how this piece of his experiment works? Is Bob really any closer to explaining how his lab equipment works? I think it's pretty clear that he's not. I think he's just looking for, just like in the previous cases, he's looking for some mathematical object which just has a one-to-one sort of pattern matching with what's going on in his lab. And I think you need more than that to explain what's going on here. I think Bob needs to bite the bullet, do what he's been unwilling to do, and give us a QFT-compatible model of his detection process. Right? So I just want to reemphasize here that the root cause of Bob's issue is an unwillingness to give a concrete QFT-compatible model of his measurement device. Now, that's the root cause issue, I'm saying. Superficially, this shows up as mathematical blunders, which either violate the central commandments of relativity, or rather they disrespect the local algebraic structure of the quantum field theory, which is, as I mentioned, now type 3 instead of a type 1 von Neumann algebra. But even if those mathematical issues hadn't shown up, if somehow Bob's hand waving did not get him into trouble and he wasn't caught, the mathematics didn't say, I've caught you red handed, right? He would still be having this methodological issue, which is the ultimate cause of these mathematical blunders if they were to show up. Right? So, really, he needs to model his measurement device. So this leads us on to the next section where I'll talk about a tale of two detector models, about the Unwit-DeWitt detector and the Fuster-Wirch detector, or the Fuster-Wirch framework, I should say.